Can you hear my voice? All right. Let's begin our class now. I'm TA Under. Today's session is about the autoencoders, right? Please make sure to download this material from Classroom. Today, okay. Is it clear now? Okay. Today, we're gonna start by constructing a simple autoencoder architecture and then move on to build a denoising autoencoder. First, let's bring in some essential libraries like torch.nn, optimizer, and transforms data loaders, and matplot library for visualization. And we'll define the model's hyperparameters at the beginning. Batch size is 256, and learning rate and number of epochs. Yeah, and for today's session, we're gonna use the MNIST dataset, run this code to download the dataset. And we'll split the training dataset into training and validation sets in a random manner using the torch utils data random split. And these are the number of train and validation sets. Of course, we can check. Then yeah. And we can know the size of the image by indexing this like this. So the first index is about image and second index is for label. Yeah, in this case, image size is 1 by 28 by 28. Of course, it's MNIST, and the label is 8. And let's also define the data loaders. Remember to set shuffle equals true, shuffle is true for the training data loader, right? Yeah, it's okay. Yeah. You're right. It doesn't matter because it is. It is the same data set, yeah. And can you guess why 196 comes from? Why the length of data loaders train is, yeah, all right. Joe is right, yeah. Yeah. And now let's move on building the autoencoder. there are two major sections, the init function and the forward function. Do you guys remember MNIST image dimension, which is 784? This grayscale image is our input. So our compress this into a latent factor of our desired dimension, 130, and then symmetrically decode the latent into the original dimension. So implement this code block on your own based on the dimension provided. I'll give you 5 minutes, and after that, we'll go over the answer together. Let's get started. If you have any questions, you can chat. That's a good question. Actually, you need to consider the final activation. It's maybe hint. No, it's not bonus. It is mandatory. We have to implement this code your own. Okay, time's up. The answer is like this. The first layer should obviously map from 28 times 28 to 100, right? Okay. Oh, I think it's too long. We can fill right now. Sorry. This is 28 times 28, 100. And this is ReLU. I use ReLU. And what's this number? Yeah, 100, comma. Yeah, 3. You're right. Oh, I think I should just copy and paste. And decoder is symmetrically written, 30 to 100 and 100 to 28 times 28. Yeah. I think wait a minute. Oh, Yunji asked, activation function should be symmetric, but actually it's not. I use sigmoid. Only the final activation function is a sigmoid. Can you guess why? Multiple answer, yeah. Oh, yeah, Uso is right. Yeah, Youngsun, Uso. Yeah, I think many people gives right answer. Since autoencoder, we want to input and output would be the same. And in our case, input is the tensor. So let's check. Yeah, this is the pixel value of first image, and we can check this min and max value. So we can see the min and max is 1 and 0 and 1, and the output should be 0 to 1. Yeah, everybody are right. And for the fourth function, we need to reshape input into a 784-dimensional vector termed x. And once x passes through the encoder, we got a latent factor encoded. And this latent factor goes through the decoder, which yields the reconstructed output. So the key is we have to reshape this tensor using view function or reshape function. Okay. Do you have any questions so far? Okay. It's not a binary classification. So why we have to use sigmoid activation function instead of softmax? Actually, the pixels are not follow the softmax distribution. Softmax has some of the softmax should be 1, but in our case, our input is image and output should be the image too. So pixels can range 0 to 1. So we use these sigmoid. Okay. Oh, it is direct message. The question was why we use sigmoid instead of softmax. Okay. And then I highly recommend using GPU over CPU in this session, given the significant speed advantage of the GPU. Wait a minute. I have a question from Hyunmin. Why x.view not? You can use 1 here, but not actually. You can't use, since this x coming from using batch, maybe x shape is patch size by 1 by 28 by 28. But if you set this number as 1, yeah, it's not match. I mean, it's okay. Yeah, minus here of this should be batch size. And when we write -1, it can automatically assign the batch size. Okay. What if our input is not in 0 to 1? Do we have to convert input into the range? I think there are 2 options. You can change your input, or just you can change the final activation layer to range from, for example, -1 to 1. Can we also write batch size? Yeah, of course. Okay. Let's move on. Here, we'll define the loss and optimizer. We're gonna use MSE loss and Adam optimizer. And let's move on the training process, okay? Again, you've got 5 minutes. Fill in the question mark in this code block. Okay, let's go. Okay, time's up. Set model to train mode. What would be answer? Yeah, model train model. And this is model eval. Yeah. And transfer inputs to GPU. How can we do? Yeah, inputs to device. Yeah. And 0, the parameters gradients, because we have to flush. Oh, yeah, we have to flush parameter gradients for every iteration. Yeah, optimizer dot 0 grad. And we need to update the parameters when the training phase. So we need to calculate the rows and backpropagation and perform gradient descent for a step. So what would be the answer? Yeah, criterion, outputs, and inputs. And how to backpropagate from the lows dots backwards, yeah. And what would be the answer for perform gradient descent? Optimizers step, yeah. And we calculate the rows for iteration, and also we can calculate epoch loss. Yeah, I hope this stuff is deep learning basics. I hope it's familiar to everyone. Okay. So I just copy and paste just in case. Do you guys have any questions so far? Okay, then run this code. And maybe this phase took about 1 minute, so I'm sorry. Ah. Yeah, maybe it took 1 minute, so please implement these question marks for the subsequent code. I'll give you about 3 minutes. Wait. Wait a minute. There are questions from Ursu. Is it right criterion outputs inputs? I think label is right. Actually, we use MSE loss, mean squared loss between outputs and inputs because we want to reconstruct the input from outputs. So input should be, no, output should be the same as inputs, not label, right? We want to reconstruct MNIST image. Not, we are not going to classification. Also, is it okay? And when I meet type error, value is not all. Should work. Oh yeah. Do you have still problem? Need to try better. Hyunmin, did you solve the problem? And label is useless in this. Yeah, in this example, label is useless. You're right. I get this error. All expected alt tensors. Yeah, this is. Oh, your guy is great. I think Ardo should write this sentence, input to input device, and also model autoencoder to device. Make sure these two lines, and you can solve it. Can you upload your? Yeah, I will upload this solution code in Classroom. Don't worry. Oh. Okay. Both lines are there, but you have the problem? Wait a minute, Aldo. Why should I multiply inputs calculating running rows? You mean this line, right? Okay. This is because we calculate loss at once from batches, different batches. So this loss came from batches, not a single image. So we multiply this input size 0. It's the same as batch size. And this is important, not that important, but input size, this batch size can vary in the for iteration. We set 256, but we have 50,000 samples. So let me show you. Okay. It can be different for iteration since the last batch is 80, not 256. So yeah, it is clear to multiply this batch size. Yeah, I think Suji is okay. Okay. And what is other answer? Other question. What's the difference between reshape and view? Oh, yeah. I think this question is good. Do you guys know what's the difference between view and reshape? I used view here to reshape 2D array to 3D array to 1D array, right? Oh, yeah, you're right, but it can be 80 or 256. It's the same, but you're right. Yeah, Junyoung is right. View is in place. As I know, there are differences in terms of memory allocation. View and reshape both can transform the dimension into desired dimension, but yeah, Sarah, you're right. So for example, A is torch length and well, this. We can transpose, right? And when transpose, wait a minute. When we transpose these A tensor, it didn't change a memory allocation. It just changed the tensor, not memory status. So in this case, we called this status is non-contiguous. So when the tensor is non-contiguous, we can't apply view function like this. V점 view. And this gives error because it's not compatible since this tensor is not contiguous. So we should use reshape. Yeah. So Songyeon said, literally change the way you shape and return it while keeping the memory structure intact. Yeah, reshape is to change. Yeah, reshape changes the memory location and also change the tensor's shape. So there's no error, even though tensor is non-contiguous. Okay. What happened if we just omit? Okay. Oh yeah, don't lose scale. We just omit model.train. This model.train when we use model.train mode, the batch normalization layers can use current mini batches mean and variance to normalize the activations. And also we can use dropout, which randomly zero out a fraction of activations. Is it mandatory? Yeah, I think it should. It is mandatory. It is yeah, mandatory. You're right. Everyone use this line. Yeah. Hey, one other question. I got type error, missing input. I think you got error right here, right? Yeah. Sangyeon, thank you. Let's move on. Do you guys trained this model? Okay. But just in case, I'll wait for one minute. And fill this blank, please. You wrote input. Okay. And can you check this function? Did you write X in here? Diane? Do you write X as input for forward function? Okay, I try base code. But I can shoot. Ah. Right. Okay. And let's move on this part. Okay. Okay. What would be the answer of this? This question mark? Yeah, train loss history. Yeah, you're right. And how about validation loss history? And X label should be the epoch, and the Y label should be the loss. Yeah. And this is for legend and show. So the answer might be, oh, like this. So I can share this code. 준영, yeah. Great. So we can observe both training and validation loss curve decreases over epochs, right? I already copy and paste the class autoencoder. Is it okay? From the learning curve, can we conclude that it already converged? Do we need more epochs? It's a good question. Usually, when validation loss are saturate, if the validation loss is saturate, we can stop the epoch. Maybe it's convention. Yeah. Oh, thank you. And we visualize the training and validation loss curve. How about test set? And let's also check the model on our test set. Then the loss is like this. Then we can conclude model can generalize well, since test loss is similar to close to train and validation loss, right? And we're gonna visualize the latent space. Before that, we can visualize our input and reconstructed output at the same time. So actually, the output is a little blurry, but we can recognize it's the same. They're the same. Yeah. I should run. And now we're going to visualize the latent space. There are multiple ways to do this, but we're gonna use a popular visualization technique called t-SNE. And first of all, we can access the raw data values using the data function, which range between 0 to 255. So to align them with the model input value, we need to normalize them by dividing 255. Or we can also check the number. Yeah. These are our test set array, right? And we need to transform the type int to integer to float and move to tensor. And this is the best model we've got trained. And this is the latent vector and the reconstructed output, right? So just run this code. As you can see, we just extract the latent factors and fit for t-SNE, right? And we're gonna visualize this output. Oh, it took some time. Yeah. Did you get the figure? Okay, great. Since we assign colors based on the labels for visualization, the result look like this. We assigned color as labels, yeah. And we can make this figure a bit prettier using these kinds of code. Someone said label is useless, but when visualizing this, we use the label. So the numbers cluster pretty well amongst themselves. And with this sophisticated visualization, we can clearly see the number ones clusters together and the number fours are clustered together, 8, 2, yeah. Okay, still loading. I can wait. Yeah, I can wait. t-SNE run on CPU. Is there any way? Yeah, maybe it can run on GPU. Yeah. Oh, good. Minte is, it's okay. Yeah, it can vary from people. Yeah. Could I ask why does the attribute CPU happen? Since NumPy array is arrays in CPU, not GPU. It's not tensor. GPU. 많이 달라 보여서요. But Minte, I think the cluster is well. And I ask why. I think Hyunmin, is it okay? And how can we interpret the difference in cluster position from one another? My clusters were formed too, but some cluster might be closer. Oh, wait a minute. I think it's different. I think it's different because of seed, internal seed. But as you learned on Tuesday, the t-SNE can't consider the global features. Maybe that's why. Okay. Let's move on. Lastly, we'll explore the denoising autoencoder. In short, denoising autoencoder corrupts the input, then autoencodes the latents, aiming to match the original input, right? This means the model's architecture remains the same. So it can use the existing autoencoder structure like this. And maybe this is the last assignment for you. I'll give you 5 minutes, but before that, I want to give some instructions. You can copy and paste this train model. This train model function. Okay, and then you can refer back to the code provided above, but there are a couple of things to change. First, you should corrupt the input before feeding it to your model. And second, the model's output should be close to the original input, not the model's input, right? Because this is the denoising autoencoder. And also we give a hint. When corrupting, add Gaussian noise to the input, just like in the provided code. Okay, I'll give you 5 minutes. Let's go. There are questions. Wait a minute. So it means we can't use Disney to assess if one cluster has relations with another. I don't think it'll be, it can't be say, I don't think it'll be easy to say that clearly. But if you want to consider global representation, I recommend using UMAP. I think you heard UMAP from last class. And question from Suji. When calculating running rows makes sense, then output out of this for loop, we can calculate the apoplos. So this is summation. Apogloss equals running loss. Running loss is summation of every epoch. So we just calculate the mean of loss by dividing the length of data orders. Okay. And Ardo, I still have the device bug. No. Okay. Well, thank you. Yeah, okay. Yeah, I think time is up, right? And copy and paste. Quote. So you need to modify this, right? We need to add some noise to input. We need to corrupt the input. So as I mentioned, yeah, we can add noise like this. So copy and paste. And the corrupted input equals input plus noise, right? And what else you should modify? Model? What means model? Yeah, input for model. Yeah, input for model is right. We should model noisy inputs. Yeah. And also, you should note the criterion, the input of the criterion is also input, not noisy input, right? Yeah, Jae-sung is, yeah, you're right. Then when you train this in this manner, oh, wait a minute. Why we need, I'm sorry, wait a minute. So it's more like data augmentation. Yeah, kind of data augmentation, but if the task, if the purpose of task is denoising, like in the field of medical imaging, then maybe it's not just like data augmentation. It's just task for denoising. But you can think in this case, kind of data augmentation. And why we need normal noise this line? Since this is initialize the noise tensor into have mean 0 and standard deviation, 0.1. Yeah, to generate a Gaussian noise, right? And you can change the variance instead of this value. It's your hyperparameter. Right. Yeah, Sangyun. Cedric, yeah, you are right. And Jae-sang. Oh, noise. Yeah, it's just code. Yeah, great. And yeah. So when we trained this model and plot wait a minute. Before I answer to someone, please run this code to train the denoising autoencoder and fill this question mark in this code block. And someone? What happens if I pass not the encoded input, but just a random noise through the trained encoder? Trained decoder. Would the result be meaningless? Yeah. I think the input is totally different from what the model saw. So maybe the result is a disaster. And these kinds of concept will be learned on next week. VAE, yeah. Okay. Did you guys train this model? Okay. Good. And it is the same. Yeah. We just copy and paste. Yeah. It is the same from this. From here. Yeah, from this, right? And what? Oh. And also it can generalize well on the test data. And when we visualize the model's input and output, of course, model input is quite noisy, and the output is the noise version of the input, cleared version. Yeah, and they look almost same. Okay. I think I've already answered this question, Jae-sang, but I can answer again. Since this loss, wait a minute. This loss came from batch, not a single image. So this, we need to multiply the batch size. And also, even though we set the batch size 256, but the last batch may differ from the batch size we chose. So yeah, it is clear to multiply the batch size here. Okay. All right, I think that's all today's session. Do you have any final questions? Okay, and what time is it? Okay, thanks for your participation, and I'll see you in the next session. Thank you.